First, I would like to thank Chris and Nigel for putting together this nice workshop. So I realize John's talk and my talk are about photons. So I have also some review of the works that has been done in the photonic systems. And please ask questions. So as much as I have time, I'll go through the talk. But if not, you can come and ask questions later. So the outline of the talk is the following. I'll review a little bit our progress that we had on synthesizing gauge field in ring resonators, how we can make synthetic gauge field, and how we can measure topological invariance for non-interacting systems. So it will be similar to what John was telling you a little bit earlier. And then once we add interaction, what kind of physics we expect, and what are the challenges and interesting opportunities we have with photons. Then I'll tell you a little bit about our progress taking these ideas that we had in ring resonators, bringing them to topological photonic crystals. And then in the last part of the talk, I'll tell you how we can actually measure interesting many-body physics in an interacting system. This is a little bit related to what Fabian, for example, was talking about. If we have a quantum system and we want to measure topological character, how we go about that. Or in general, if we want to characterize a topological property of the system, how we should find an efficient way. Okay? So the first part was synthesizing gauge field in photonic systems. The building block of photonic systems are basically resonators and sites. So here you can think of ring resonators on silicon dioxide, silicon rings on silicon dioxide. These are actually made of waveguides. So the photonic or the Maxwell's modes are confined in these dielectrics. And if these two dielectrics come close to each other, the electromagnetic wave can tunnel from one waveguide to the other waveguide. So if you put a bunch of them next to each other, the photon will hop from this resonator to the next resonator, etc. Okay, so you can 1D array of it. You can think of it in also exciton polariton system that you can make gallium arsenide coupling to light and then pattern the system. So then the polariton will hop from one side to the other side. So a while ago, we thought about how we can synthesize a gauge field for these arrays of photons. The problem with photons, especially in the optical domain, is that magneto-optical properties are weak. So if you put a magnetic field, they won't really see it. Okay? So if they don't see it, we have to synthesize it. Similar to neutral atoms. Neutral atoms don't see the charge. We have to synthesize the magnetic field. Here, we do the same thing. So the essential idea is that if we have a 2D array of ring resonators, we have to get a phase when we go around the plaquette. Okay, so more formally, we have to have the Hofstadter Hamiltonian that we have seen many times. And if we manage to imprint a phase when a photon goes around a single plaquette, then we are done. Okay? So the way that we came up with a while ago was that we coupled two ring resonators with another resonator that is off-resonant with them. Okay? In particular, if this resonator's length is m is an integer, lambda is the wavelength that we're interested in. If I choose the middle resonator to be m lambda plus lambda over 2, then it's exactly anti-resonant with these two. So if a photon starts to circulate around this resonator, it comes here, it gets scattered, and then goes up, and then comes here. It won't continue its way back because it's interfering anti-resonantly with itself. It's a destructive interference. So instead of going back, it will go into this resonator and it spends some time, and then it comes again into this coupling region. It gets scattered. Instead of now going many times around this, it will only take the lower path. So when I hop from left to right, I take the upper path. When I hop from right to left, we take the lower path. And if I move this middle resonator and put it in an asymmetric way, then the accumulated phase that the photon takes from going left to right and right to left are different from each other. Therefore, if I write an effective Hamiltonian for this hopping, I'll go from left to right, I take some phase. When I go from right to left, I take another phase, but they should be exactly opposite to each other because We have not broken the time reversal symmetry, and the Hamiltonian should be Hermitian, so these two phases should be opposite to each other. Is that obvious? Good. Okay. So if we have this, then we can actually change this phase for different rows or different columns. And
plays the role of a spin, two polarizations.
Yeah. Okay. So that's a subtlety that I didn't want to get into, but now Bert asked the question. So we have not broken the time reversal symmetry. It sounds strange that we have a magnetic field. The reason is that we have two spins, basically, two pseudospins. One is the polarization that goes this way. The other one, the polarization that goes the opposite way. Okay? So I just told you the story for the spin up, let's say the photons that are going in this direction. They would see, let's say, positive magnetic field. And now if I look at the photons that are going in the opposite direction, if they want to hop from left to right, they would take now the lower path. So they would see the opposite phase. So spin up will see uniform magnetic field. Spin down will see the uniform magnetic with opposite phase. Exactly like the BHZ Hamiltonian for quantum spin Hall effect. That we have two copies of quantum Hall effect, two time reversed copies of each other. But here, we assume that we just excite the system in one of these modes, and we stay in that mode. So by symmetry, we're staying only in the half of the Hilbert space. And if there is no scattering process that takes us to the other part of the Hilbert space, then for that specific part, we have effectively broken the time reversal symmetry. Does that answer your question?
Yes.
Okay. So now we have the Hofstadter. If we send the photon exactly at the edge, the photon should propagate around the edge. If we send the photon at the bulk energy, then we go into the bulk. Okay. So we did the experiment using silicon on insulator technology. So this is the array of ring resonators coupled to each other. So these are the main resonators, and this one is the link resonator, which is only off by lambda over 2. Lambda here is the telecom wavelength, 1.5 micron. So on this scale of 30 micron, you can't see the difference between the main resonators and the link resonators. But they're just off by lambda over 2. Now, if I excite the photon in that specific energy, then the photon should go around the edge of the system. If I excite it in the bulk, it should go into the bulk. These resonators are not perfect. They scatter light. So if you put a camera, we can actually see where the photon is propagating inside this material. Okay? So in particular, if I tune my frequency to be in one of these edge modes, I propagate around the edge of the system. So this is the simulation. This is the experiment. In the simulation, I expect that it would be smooth. But since it's a finite system, the edge state is not uniform. It has some mode, basically. In the experiment, it's similar as well. It's not uniform, but it propagates only around the edge. Okay? So similar, again, to integer quantum Hall, if we have some impurity in front of the propagating edge, the photon comes in. So here, the impurity is that we removed one of these resonators intentionally. So the photon comes in. It will see this obstacle. Instead of getting back scattered, it will go around the impurity and then continues its way. And that's what we saw in the experiment. Okay? So in this sense, these systems are robust only to this on-site potential disorder. So they're not robust against loss. They're not robust against backscattering that will change the spin if the effective sigma x or sigma y Zeeman field in the system, plane field in the system, but they're robust against the impurities of potential type. Okay, so one can also look at the statistics. We can repeat the experiment many times for different. Yep.
So for the pictures in the previous slide, should I think of this if I want to map this onto like an atomic picture?
Mm-hmm.
That this is averaged over many different times for the experiment?
It's CW. It's CW.
When you take a picture of this, if I wanted to map this onto, say, preparing the same initial state and then evolving it for some amount of time,
Mm-hmm.
is the analogy here that I'd be averaging over that final time with the initial state?
That's right. That's right. That's right. Yeah. But your preparation time should be long enough such that the inverse of your pulse width fits into the bandwidth of the edge.
By bandwidth of the edge, you mean the set of eigenstates that are mostly localized?
Exactly, because if the pulse is so short, then the Fourier transform of it will be broad. Then you will be talking to all the states. So if I repeat the experiment for many chips, then from chip to chip, we have different realization of disorder. So we see the bulk states are very noisy from one experiment to another experiment. Different colors are different chips. We see a very different behavior. But in the edge bands, here I call them short and long propagating in the long edge of the system, short propagating around the short edge of the system. We see some robustness. So this is transmission as a function of frequency. This is the delay time, the Wigner delay time as a function of frequency. See that when we change these samples for the edge bands, they are robust. This is all integer. Okay. Then we can also look at the scaling of the system transmission as a function of system length. And we see that actually it's better than a 1D system. Okay. So there are actually many other ideas how to synthesize gauge field for photons in different colors and different frequencies, in metamaterial, photonic crystal, modulating lattices. So if I modulate lattice, I break the time reversal symmetry with helical waveguides. So these waveguides, effectively, you simulate time as propagation in Z. So basically, you effectively break the time reversal symmetry. Schuster and Simon publication company. And yeah, sorry. That should be the logo, no? Yeah, and there is a nice review by Joan Apples and Marin Soljacic. So, fractional quantum Hall. So now, no, sorry, just measuring, that was actually wrong. Measuring topological invariance with photons. So measuring topological invariance with photons, what is now, what's the manifestation of these integer prefactors in conductance for photonic systems? Because the transmission goes from 0 to 1. So what is quantized here? What is the integer? We go to Laughlin and Halperin's picture. Basically, if I have a ring geometry and I pierce a magnetic field into the system, what happens is that I should look at the edge states and how they flow. Okay? In particular, if I change phi from 0 to 2 pi, then I see some edge states will flow upward, some of the edge states will flow downward. So this is inverted. This is not the usual way that we have it in electronic systems. So this is frequency, and this is, let's say, the momentum of the edge states. So the blues are the outer edge, the reds are the inner edge. So when we change from phi from 0 to 2 pi, 0 and 2 pi are equivalent, so my spectrum should be the same. But when I'm inserting this flux, these should flow upward or downward depending on their winding. Okay. So here I assume we have only one edge state. If we have two, we have two bands, and then we move twice. Okay. So if I put my Fermi level here, then one electron will go up, one electron will go down once we pair this magnetic field. So that's the integer number. So the equivalence of that is very simple for photonic systems. What we can measure is the transmission. So we send the photon, it goes around or it goes inside the bulk, and it comes out. Now let's assume that we are sitting in the band edge. The edge frequency band. And now I change phi from 0 to 2 pi. These eigenstates should move upward or downward. So if I look at transmission as a function of frequency and I change phi, then these resonances that characterize the presence of these eigenstates should move to the left or to the right. In particular, if I change phi from 0 to 2 pi, this should move and come here, this peak should move and come here, etc. If the winding number is 2, then it should move by 2. If the winding number is -1, it should move in the opposite direction. Okay? So if we can synthesize this magnetic flux and then change the flux and look at the transmission, the number of times that we see the occurrence of this interference pattern should basically measure the winding number. It's a non-interacting photonic system, so it should boil down to some interference experiment. So the integerness is basically the number of times that this interference repeats itself. Okay. So there is the more elegant way and more general way to understand this, these properties, in particular to highlight the bulk edge correspondence. If my bulk has some topological property, my edge should have also some non-zero winding number, and also the generalization to the strongly interacting limit. And that actually can be done by going to the Chern-Simons theory. So I apologize for the experts. This is an introduction to the Chern-Simons theory. So the same way that we have Maxwell's equation in 3 plus 1D, we have the Lagrangian. We couple it to some charge. We vary. We get the Maxwell's equation. Okay, and it's actually gauge invariant. So if I change A, this capital A, by the gradient of lambda, the system is gauge invariant because f mu nu is manifestly gauge invariant. The Chern-Simons action is given by this. Lagrangian is given by this, and then I couple it to charge. I vary. What is nice about this system is that if I forget about my real electromagnetic field, like Maxwell's equation, if I vary the system and I look at the response of the system, the time component of it will fix the feeling factor in the system. This is rho, the density of charge. This is B, the magnetic field, and they're coupled by this fixed number. So this will be my feeling factor. The other one will give me the Hall conductance. But what I want to get from here is that this actually nicely reproduces the integer and fractional quantum Hall effects. There are some subtleties. There's just capital A, so there is no lower small a. But what I would like to highlight here is that this, if I look at this effective field theory, it can reproduces the response of the system. In particular, what is interesting about this Lagrangian is not gauge invariant. So if I add this lambda to the system, is not gauge invariant, and if I write it for a system that has some edge, I will end up with some extra edge there. Okay. The way that we can actually fix this extra edge term is that we should add some chiral edge state. So basically, what I said is that if I have a Lagrangian, which means a Lagrangian of Chern-Simons, which means that I have some topological bulk property, then it means that my edge should have also topological edge property. So what I said in the spectral flow that I mentioned in the analyst picture can be also seen here. How? If I just assume that I only have the edge state, I only have access to the edge, and I gauge the bulk, gauge the edge of the system, I should see this anomaly, because I should see this basically gauge anomaly. I said if we have a system that has the edge, if we gauge the bulk is anomalous. If we gauge the edge, is anomalous. But when we put them together, the whole system is a gauge anomaly free. So we can actually see this bulk edge correspondence in this picture. In a non-interacting regime, we should see the following. So we have the Lagrangian for the edge. I just only focus on that. It's a finite system, so I just get a bunch of energy states. And now when I gauge the system, I change phi from 0 to 2 pi. These states should flow up or down, very similar to the simple non-interacting picture that I gave. So that's actually exactly what we did in the experiment. In the experiment, we did not put a magnetic flux, thread a magnetic flux into the whole of the system. We only focus at the edge of the system and gauge the edge. That's why this was a little bit more relevant. Although it's non-interacting, it's valid.
Sorry, how do you gauge the edge?
So this is our chip. So this is, again, the previous one system that we had. In the beginning, actually, we wanted to thread the edge. We wanted to thread the flux into the hole, but technically, it was not possible. What we did is actually we only focused on the response of the system at the edge. And the way that we added this phase was through heating these link resonators. Remember that the length of the link resonators, the upper and the lower one, would dictate how much phase we accumulate when we hop forward and backward. Now, I only heated the top part or the bottom part here. It means that we add an extra phase when we go around the edge of the system. But we only introduce it at the edge of the system. If I introduce that extra phase on this row and on this row and on this row, then that would characterize piercing a magnetic flux into this hole, because I have to basically define a branch cut, and I add that phase all around that branch cut, and that would characterize basically the extra edge. So this is actually the experiment. So we had these ring resonators, but we had to fabricate this metal heaters that would heat the upper part or the lower part. So this is the experiment. This is the measured data. This is the simulated data. This transmission is a function of frequency. This is the one edge band. This is the other edge band, and this is the bulk band. So what we expect is that when we go from 0 to 1, so the blue is 0, 1 is red. The spectrum should repeat itself in the edge, and it's better to see it in the simulated one, that it will actually come back to the same. But sometimes it's not exact because we are looking at the finite system. So the best way actually to characterize it is to make a line here and then see how many times these peaks pass through that line. So if we make a zoom in here, this is transmission contour. This is frequency. This is change of this magnetic flux. And then we see that these edges will go through this line only once, or again, only once, but in the opposite direction. So that will give us basically the winding number of the edges. Okay. So how much time I have left?
It's another 10 minutes.
Okay.
Well, then we have still some left.
Okay.
Well, then we have still questions.
Yeah. Okay. So then if we gauge the inside, we don't see anything. We can also do some. And now I speed up. We do a control experiment to make sure that everything is correct. So everybody would believe. No, I tell you a little bit about this. So, what if I have just a ring that is non-chiral? So I have some states that go this way, but some states that go that way. If I gauge a trivial system, what should I see? I should not see this spectral flow. What we see is that some of them will go to the left, some of them will go to the right. But then when phi becomes 2 pi, they should come back to the same place. So that's actually what you expect in a trivial system where it's not chiral. So that's actually our measured data. We cannot resolve it because, of course, the forward and backward would couple to each other. There is no robustness. But the fact is that there is no net flow. If I make a line here, the edge states will not pass through it. If one passes through it through the left, will one pass through it through the right. So there is no net flow, and that's basically the winding number. Okay. So fractional. Fractional, the recipe is super simple. We get the gauge field, we add some interaction, and then we get the fractional quantum Hall states. Yes. That's and then we have it. So more specifically, we have the same gauge field that we had. Now we have to have some on-site interaction, for example. And then if U is larger than J, in the language of photon, basically means that we are in the photon blockade regime, meaning that the tunneling between resonators is smaller than the interaction on each side, then we expect that we could get some fractional quantum Hall states. So the challenges and advantages of optical systems. So the challenge is the weak interaction in optical domain. So we can easily make the synthetic gauge field as we showed and John showed and many other groups. But implementing interaction is hard. There are, of course, some advances, but that's one of the challenges. The other ones are related actually to the preparation of these systems. Photonic systems are lossy, and if we prepare it at some, if you want to prepare the system at a fixed filling factor, we are not guaranteed to stay at that filling factor. So we have to come up with new ways of preparing these systems. Lack of chemical potential, again, preparation. I cannot park my Fermi level at some specific point and then say, okay, my filling factor is this, and then I expect this. What should we do with it? Lack of thermalization. Photons weakly interact with each other. Inelastic scattering between photons is very weak. So we cannot just hope that the system will thermalize and get to the ground state. So these are some questions. What are the advantages is that we can actually, in the microwave domain, we can engineer K-body interaction. Some of this parent Hamiltonian that has been advertised in quantum Hall literature could be actually implemented in the microwave domain. We can have 3-body interaction, 4-body interaction in the absence of 2-body interaction. So it would be interesting to see this. Length scale, these are either centimeter length scale or micron length scale. So one can actually resolve spatially and do correlation function measurements in the system. So we have done some work, and many other people some work. It's an ongoing. I would like to just highlight that these are like experimental and theoretical challenges that people are facing. So, for example, interaction between photons. John mentioned Rydberg. Photon-photon interaction induced by Rydbergs. Nanostructure systems, so like photonic crystal waveguides, coupled to atoms, where the atom actually mediates the strong interaction, or solid-state emitters that again could mediate a strong interaction, and also circuit QED systems. So there is a recent actually paper by the Google team, the John Martinez group at Google, where they actually simulated a 3-site system with a synthetic H field in between. So the challenge of preparation is that we want the filling factor. In particular, there was some discussion yesterday that if nu equals 1/2 for a half filling, this Hamiltonian, when alpha is small in the continuum limit, is the exact ground state of the system, and it is gapped. But how do we prepare it? The usual way that we prepare an optical system is that we pump it by a coherent state. And the coherent state is composed of a Poisson distribution of photon numbers. 1 photon number, 2 photon number, according to the Poisson distribution. So you can hope that in some photon number manifold, you get your interesting filling factor. But then it is convoluted by the zoo of other filling factors. But if we look at actually a weak excitation, if we are in the if this beta, the strength of the pump field is very weak, then we can hope for preparation of 2 or 3 photon Laughlin state, as John mentioned. It cannot be generalized to the many-body case, but at least if we are interested to prepare a few, that's the way to go. So that led us actually to think a little bit how we can use the incompressibility of these many-body states to prepare them. So the incompressibility for photons basically means blockade. In other words, meaning that by incompressibility we mean that if we add a particle, the energy to add a particle is different than adding a particle to the system. The energy to add a particle to the system is different from subtracting a particle from the system. So can we actually use this to prepare a many-body state? So let's focus on a single site. So I have a single cavity, and it has this nonlinearity 0, 1, and 2. And I would like to prepare it in the 1 photon Fock state. If I coherently drive it at this resonance, it will not go to the 2 state because this is off resonant. But then it will go into the superposition of 0 and 1. So instead, we couple it to an auxiliary spin that has only 2 states, and we parametrically drive it, such that if parametrically drive it with the frequency that is equal to the sum frequency of this transition and this transition. So what's the consequence? The consequence is that if I start in the ground state, Then this parametric coupler will take me to these up states. And then I assume that this spin can quickly relax and come here. Then again, the parametric pump wants to take this excitation here and take the excitation over here. But this is detuned, so it will not go up. So it will remain here. And now, if this photon would like to relax and come back again, then the parametric pump will pump it and then put it up here. Okay? So this is a single site. So we showed that for a single site, by this auxiliary qubit, we can pump the system and prepare it at a fixed photon number. Okay? Now, the same idea can be applied to the many-body case. In particular, for fractional quantum Hall systems, they're flat with this short-range interaction. They're flat from the left, meaning that if I look at the spectrum as a function of number of particles inside the system, if I add particles one after another, there is no energy cost except just the energy of the lowest lambda level that I have to add every time I add a particle, until I hit the Laughlin filling factor, n equals 1/2. And after that, I have to pay a price to go up. So we can actually generalize the same system and pump this photon one after another to come here and stabilize the system. Of course, it's a steady state. It's not a pure state. And the implications of that are interesting. We can discuss that, but I would like to move on. So, how much time?
2 minutes, so 3 minutes.
Okay. Okay, so I'll just highlight about some of the progress on the topological photonic crystal. Why we're interested in that? In the ring resonator, it was interesting. We could make these synthetic gauge fields, but we would like to add this nonlinearity. And in order to add nonlinearity, it's better to reduce your mode volume such that the interaction between photons increases once we add an emitter. So we are actually translating those systems into photonic crystal. In particular, what we looked at is that we took a honeycomb structure with these triangles, and then we deformed this honeycomb structure. So the honeycomb structure has this Dirac cone at this point. And if we deform it, meaning here in particular we shrink the unit cell or we extend the unit cell, we open a gap, and it turns out that this opening a gap is non-trivial in the sense that it will invert the band. So if I look at the orbitals here, I have like a s orbital, a p orbital, d orbital, etc. And if we shrink or extend this, it would invert the band. In particular, if I have a pristine honeycomb lattice, if T1 is equal to T2, if I have this graphene structure, then we have a Dirac cone. But then when I increase, when T1 is greater than T2 or T2 is greater than T1, we open up a gap, but with an inverted band. So more specifically, we have two polarizations inside the system. We are not breaking transversal symmetry again, but for two polarizations, we get this non-trivial band inversion. So non-trivial band inversion means that if we keep the polarization and then interface two different topological systems, meaning that I invert the band one way and I invert the band the other way, we should get a protected edge. Okay, and that's actually we have simulated so far, and we hope that we could see it also in the experiment. So I'll actually I don't have time for the last part, unfortunately.
Who needs coffee?
Well, if you ask me a question about that, then I will I'll talk about it. So I would like to summarize and acknowledge and my group and collaborators who were involved in this project. In particular, the silicon photonics experiment was led by Sunil Mittal, and the photonic crystal is actually led by Hiro and Sabyasachi. Hiro actually used to be here now, and then I actually didn't talk about this. So thank you very much. So there is this square root n problem. You're saying that why we cannot increase these?
Yeah, so there was this comment that you both said that basically it's a bad way to try to prepare one of these states by pumping in just the coherence.
Okay, so I can explain it why. So when I make a weak coherent state, there is a hierarchy of Fock states. So you basically all the time, mostly all the time, you have vacuum. You have one photon and then two photon, etc. So you have this hierarchy. Then you can.
So it's just the drop off.
Yeah, exactly.
And then so then my second question is, can you be in a regime with these systems where you can post-select your data on the basis of how many photons are in there?
That's right.
Could you have like good enough protection efficiencies? Oh, I had 2 photons. Oh, I had 3. Or then operate sort of like
Can we have that? Yes, in principle, if you can post-select and make sure that no photon is lost, then you can post-select and say that I was in the specific manifold. But remember that if I even miss a single photon, then I was in another manifold.
Right. So I guess my question is more specific to that, which is, how good is the detection in these systems, I guess, across various?
I would like to answer actually your question in a different way. So far we are looking at a pristine system, and we have to say we are at this specific feeling factor, and it works Laughlin states, etc., or other states. But if you deviate a little bit in the electronic system, we say that, well, there is always this localization. If I have some excitation, they will localize. They will not contribute to the conductance, etc. Something similar may even happen in a photonic system, that you don't have to have this exact preparation of the filling factor n equals 1/2 or n equals 1/4. Maybe some disorder inside the system will come and help us, but at least I don't know a systematic way to study that in these systems. But let's say I'm epsilon away from my filling factor. Can I just hope that the same thing that happens in electrons would happen for photons?
I'm going to do it. What is this measurement?
Okay, well, no coffee for you.
He drank the poison.
So the big question was that what's the efficient way to characterize and measure a many-body system? And one of these characterization is entanglement spectrum. Hope many of you are familiar with entanglement spectrum. So we cut the system in two. We look at the density matrix. The density matrix can be diagonalized, and we can write it in this way. And this is the entanglement Hamiltonian. The question we asked was that can we actually measure this the spectrum of this Hamiltonian? It's a spectrum. So we should do the same thing that we do for a normal spectrum. So if I want to find the spectrum of a density matrix, we can do it by reminding ourselves what we do exactly to find the spectrum of a Hamiltonian. So in order to find the spectrum of a Hamiltonian, I should have access to e to the minus iht. Okay. So if I have access to e to the minus I rho t, then I can get the spectrum of rho. That's it. So how do we do that? We use a trick actually that was introduced by Sitloit and company, that if you have a global swap operator, if I have two copies and I take rho 1 and rho 2, and then I apply this e to the I minus I epsilon s, where s is the global swap operator, to the first order in epsilon, it's as if rho has evolved with the other density matrix. Okay? And then we figured out actually a way to really do this, because it needs a global swap, and the global swap is not easy, but it turned out that you can do the global swap by just dispersively coupling an ancilla to part of the system, and not only make that global swap, but also read the spectrum of the system from that ancilla. The spectrum is a bunch of real numbers, so in the end, I can just read it through some Ramsey spectroscopy of this ancilla. Sorry, I'm not giving all the details, but that's the big picture. That we do basically Ramsey spectroscopy on this ancilla, and then it extracts the spectrum of the entanglement.
Okay, so I will not allow further questions. Before we thank again, I just realized, I read the program and I realized something I think important for the first speaker of the afternoon session. I think the afternoon session starts at 1:30 and not at 2 o'clock as we're used to. Just
So at least the speaker needs to be here.
of course. Okay, but let's thank